Let's welcome everyone. Is this working? Yeah, okay. Quick recap from last time. So we talked about maximum flow, how to compute this maximum flow in such a network where we're given a source and a sink and capacities. And we had an initial idea how to do that. We looked in each step sort of for a path from the source to the sink along which we could sort of push extra flow. And then we saw if you do this in a naive way, we might not find such paths, even though we saw that this is not the optimal flow. And so we found out that it's a better way to find these paths in the so-called residual network, not in the original network. And we did that and came up with this algorithm by Ford and Fulkerson, which starts from the empty flow, and then in each step creates the residual network and finds a path from S to T in the residual network, pushes more path, more flow until it cannot find any longer any augmenting path in this residual network. And we talked about the running time briefly of this algorithm. And then we wanted to know, of course, the flow that we end up with after all these iterations. Is this really the best we can do? So the flow that we end up with after not being able anymore to find an augmenting path, is this the optimal flow that we get? And so we tried to do this by linking it to the capacity of a cut. So we said that we can upper bound the value of a flow by the capacity of a cut, and we did this by first connecting the value of a flow based on the original definition of just looking at what's leaving the source minus what's coming back to the source. We linked that definition of the value of a flow to the net flow across a cut. We had this sort of a relatively long technical proof showing that the value of the flow is equal to the net flow across any cut in the network. And based on this relationship, we could show that the flow value is actually upper bounded by the capacity of any cuts in this network through this intermediate step. And that's a very good thing, because now if you're able to find a matching cut, meaning a cut with a capacity that is equal to the value of the flow, we know that this flow is sort of the best possible. And that's in fact the case according to the max flow min cut theorem. This is where we ended, at least by stating the theorem, which said that if you're not able to find such an augmenting path anymore, then we have found a matching cut, or we can construct a matching cut, and that means that the flow that we ended up with is actually the maximum possible. And so this is what we're going to prove now. The proof is very intuitive, so it's a good way to practice sort of the definitions and relationships between these different concepts. It's not so technical as the previous proof from last week. So let's start with the proof of this theorem, and this is really the central theorem of this chapter. How to increase this height? All right. So here's the proof. And so we want to show the equivalence of 3 points, and we do this by showing implications from 1 to 2, 2 to 3, and from 3 to 1, which establish this equivalence between all three. So we will prove that from 1 follows 2. I mean, from statement 1, so I'm referring to these numbers up here, that from statement 1 follows statement 2, from statement 2 follows statement 3, and we will show that from statement 3 follows statement 1. And this is, and this means that we have shown equivalence between 1 and 2, and between 2 and 3. That's our strategy, and you'll see that 1 are sort of completely like obvious. 2 steps are, it's one sentence. It's the critical thing is really this implication here from 2 to 3, that once we cannot find any augmenting flow, that we have sort of that we can construct a matching cut to that flow, and that means that it's optimal. So let's see. But let's start easy with this first implication from 1 to 2. And I think this by now should be clear to everyone. If F is a maximum flow, there can't be any augmenting path. Why is that? Because if there was an augmenting path, we could use that to increase the value of the flow, as we demonstrated before, and that would mean that the original flow was not maximum. So it's follows immediately. I'll write it down anyway. So say that F is a maximum flow. And that P is an augmenting path. Since any flow along this augmenting path would increase the flow, the flow F wouldn't be maximal, which is a contradiction to the assumption. Since any flow on P would increase the flow, F wouldn't be maximum. This is a contradiction. Okay, this was a warm-up. Now, much more interesting is really this relationship from 2 to 3. We want to show that if the residual network has no augmenting path, and this is exactly when we terminate in the Ford-Falkersson algorithm, then F, the value of the flow, is equal to the capacity of some cuts in our network, which we will have to construct. And that's actually what we will do as part of this proof. So to prove 2 to 3, let's say there doesn't exist an augmenting path in the residual network. And this is our claim 2. So say there doesn't exist an augmenting path in the residual network, GF. The central idea is to look at all the vertices, all the nodes in this network that are reachable from S, meaning for which there exists a path from the source to that particular node. So let's define that. So let's call that L, set L, be the set of all nodes. Nodes. No. U and V, with U is reachable from S. And R is simply the rest, so FV minus L. So this is sort of a partition we define on the residual network. Let me visualize this. So let's say we have the residual network, which will at this point look like this. We have our source, and from this source we can reach certain vertices, and then there will be a gap, and then there's other vertices that are probably connected to our node T. And then based on this definition, we call this capital L, and this will be capital R. So this is how we define these two node sets, L and R. L is simply the set of nodes that we can reach, and R is the rest. And that means that if you look at the edges that could go from L to R, there basically isn't any, right? We can't have any edge in the residual network that goes from L to R with positive residual capacity, because if we had such an edge, then this edge would basically connect this vertex to some vertex in L, and therefore this vertex would be part of R, but it would also be reachable from S, and therefore it should be also in L, which is a contradiction. So that cannot be, just based on our definition of sets L and R, there can't be any edge with positive residual capacity from L to R. So I think this is easy to see. So by the definition of the set L, you can't have any edge with residual capacity CF UV strictly greater than 0 for U in L and V in R. Right? So this is just based on our definition of LR. There can't be any such edge because a bit more formally, why can't that be true? Because then this vertex V in R will also be part of L because it's reachable from S, and therefore the intersection between L and R would be non-empty. So V would be in the intersection between L and R. Here's our contradiction. And therefore, because of this contradiction, we can conclude that the residual capacity of all these edges from L to R must be 0. Okay, so hence residual capacity of UV is equal to 0 for all U in L and B in R. So far clear? Any questions? Yeah. Say there doesn't exist an augmenting path in the residual network. Okay. So this is what we had. Sorry, yeah. Then V element L intersection. So it's both in L and R. And this is not how we have defined it. So we defined L and R, I mean R to be everything but L. But if you had such an edge, then let me actually illustrate this or add this to this figure. So if you had such an edge from anywhere in L to R, all these capacities, these residual capacities on these edges must be small. All these residual capacities of such edges must be 0. This is purely based on the definition of L and R. There's no magic trick so far. Okay, but let's see what that means. So let's go back and look at the definition of these residual capacities in our residual network, and then we'll be clear where we're aiming at. So the residual capacity, sort of as a reminder of UV, is defined as follows. So this is nothing new. We did this before. If UV is an edge in our original network, what is the residual capacity of that edge? Just as a practice, does anyone tell me what the residual capacity of such an edge would be? Just a definition. Yeah. Yeah, exactly. Capacity minus the flow. This would be simply the capacity of UV minus the flow UV. And if we have the reverse edge in our graph, So if VU would be in E, then what's the capacity, residual capacity of UV? Yeah, exactly. It's the flow from V to U. And in all other cases, it's anyway zero capacity. So let's look at these two cases. The first case, call this case A. We have that CUV must be equal to F, right? Yeah, which is true. Let's say that C minus F UV must be zero, and therefore the capacity of CUV must be equal to the flow. In B, case B, we have that F VU must be also zero. So to get this here, I simply took the definition of residual capacities and connected with the observation that all these capacities, these residual capacities from left to right must be zero by the definition of our partitioning into L and R. And if that's the case, if all these residual capacities are zero, two things must hold. A, edges from left to right have to be completely saturated, meaning they have to have flow equal to the capacity. Otherwise, you would have an edge with non-zero capacity. And in the reverse direction, if you have an edge from right to left, there must be zero flow, because otherwise you would create the reverse edge in the residual network with capacity equal to the flow of that edge. So this is what these two things say, and then we just plug it in and we're done. So let's write down the value of a flow, just a definition of a flow. We said the definition is equal, the value of a flow is equal to the net flow across any cuts, and therefore also across the cut LR. So this is the same as saying net flow from L to R. And by the definition, F of LR, I'm simply summing up over all pairs of nodes from left to right. So U and L and V and R. F UV minus everything that comes back from the right to left. Again, U and L and V and R. F of V comma U. So this is just a definition of the value of the flow using the theorem from last week, where we said the value is equal to the net flow across any cut. In our case, it's a specific cut, namely cut from a bit between L and R. And the net flow is simply defined as the flow, everything from one side, from left to right, minus everything back from right to left. This is what the value of the flow is. And so now we can plug in basically our insights here, what we have defined, what we have derived from the residual capacities being zero. So this term here, can anyone tell me what happens with this term here on the right if I sum up all the flow that comes from right to left? I think I heard some here. Say again. It's the flow from R to L, but how much is it? I mean, what's the value of that flow? It has to be zero, exactly. So this is basically what's written here. This is what we said. If we had a non-zero flow here, we would create this edge in the reverse direction with non-zero capacity. We don't have this. This is based on the definition of L, and therefore this term here on the right just zero. So this here is zero. And what happens to this term? From left to right, the flow, what's the value of the total value of the flow from left to right based on our observations so far? it's right here. Just have to read the right thing. Yeah. CUV. Yeah. So it's exactly the same as the capacity. That's what we said here. That from left to right, all the flows are equal to the capacities, and this is basically what we get here. So this is here. This one here is simply the capacity of UV. So if you write this down, and this is the same, simply as just summing up capacities of all edges from left to right, CUV, which is the definition of the capacity of this cut. So this is the capacity of L, R. And that's what we wanted to show here in this part, 2 to 3. We wanted to show that if there is no augmenting path, we can create this partitioning into L and R using this reachability idea. And we showed that in this particular case, the value of the flow equals the capacity of that particular cut. And as you will see in the next step, this means that it's also the optimal flow. But for now, we have just found a matching cut for our given flow. Is that clear to everyone? Maybe you think about it while I'm writing it down and have more questions. Okay, the next part. Everything clear? So this is the heart of this proof, just knowing how to construct from this flow a matching cut. Matching cut meaning a cut with the capacity being equal to the flow of this of the value of the flow. And based on what I've said before, actually, this means that this flow is optimal. This is just have to write it down now, based on we said this somewhere here. Last time we said that the value of the flow is upper bounded by the capacity of any cut. And now we have found one cut that is equal. And from that, we can conclude that F is equal to C. So by this corollary, 26.5, we know that the value of the flow is upper bounded by the capacity of any cut. So this is true for all cuts, LR. And so the fact that we found one that is equal, that the value is equal to the capacity, implies that F is maximum. Does everyone see that? Any question about my spelling, writing? All but? Cuts, for all cuts? Yeah, it says for all cuts. So the value of the flow is upper bounded by the capacity of any cut in this network. We have found one that matches, and so we know that F is maximal. So let's go back to our example. Here, this one. Here we ran Ford Falkeson on this network, on this one here. And we came up with a flow of value 23. So now to prove that this 23 is the best we can do, we have to find a cut in this network with capacity 23. And we can do this visually, and we can probably find it even just by eye in such a small network. But now in this, as part of this proof, we also have seen how we can actually do this systematically by looking at all vertices that are reachable from S. So let's see if this is true. I'm just copying this network real quick. Okay. And for this network and for this maximum flow, we had this residual network in the very end. And so according to this construction and proof, what we have to look at is is all the reachable nodes from S in this residual network. In this particular case, the nodes that we can reach from S is this one here, and we can reach this one, and we can reach this one, and we cannot reach any other nodes. Any other meaning none of the two others. So that would imply a partitioning of this set of vertices that will look like this, right? So I have these 4 vertices in one set in L, and I have the other 2 vertices in R. Let me just draw this down or paste it. This is our original flow network. Make things a bit easier just to read. I will just remove these flow values. We don't care about this, but we do care about the total flow value, which was 23. And the remaining numbers here shown are the capacities. And so we said we would look at the following cuts. Namely this one here. So this would be L in our case, and the remaining 2 vertices will be in R. And what is the capacity of this cut? I mean, we know what it should be according to the max flow min theorem, the min cut theorem. This here, capacity 12. We have capacity 7 here is 19, plus capacity of 4 is 23. Yeah. So the reachability is defined based on the residual network, not on the original. This, what I'm showing here, is the residual network, the original. And reachability in this proof we did in the residual network. And the residual network is this one here. So this is the residual network that corresponds to the maximum flow of our original network. And so the only thing I have to do is find which vertices in this residual network I can reach from S, go sort of traversing edges in their direction, which would be this one, and this one. And I can't reach any of the other 2 vertices. And this is how I create the cuts. And then I simply add up the capacity of all edges leaving this cut or leaving L, which in this case is 12 plus 7 plus 4, which is 23, and therefore equal to the value of the flow. Yeah. Because 9 goes back. I mean, not in terms of capacity. So the capacity is defined based on the capacities of all leaving edges. So this is written here. Whatever you call it, but in the end, this is what we get in this equation, and this just sums up the capacities going from left to right. Any other questions? Okay, so let's just write this part down. We got what we wanted, namely that the capacity of this particular cut here in this example is equal to 12 plus 7 plus 4, which is 23, and therefore equal to the value of the flow. One more example, because now, can we say anything about the cut? So we said that we found matching flow and cuts, and therefore we concluded that the flow is the maximum possible. What about the cut? Can you make any claims about the capacity of the cuts that we have constructed in this matching example? Idea? Think about this upper bounding idea. Yeah, exactly. It's the cuts with a minimum capacity, because same arguments, the capacity of every cut is an upper bound. We have found that matches a flow, so there can't be any cut with a smaller capacity. Yeah. And we have also seen now how we can compute such a cut or the capacity of such a cut, namely simply by creating the residual network. looking at all vertices that we can reach from S, and then we're essentially done. We just take the capacity of this particular cut. So let's do one example here for computing the minimum cuts given a network and given a maximum flow. This is the same thing, just reversed. This just for illustration, we want to find the minimum cuts of the following flow network. And we assume that we're given the maximum flow. Let's say this is our network, G. It'll look like this. We have a source. We have two vertices, E and D. And the vertex C. And our sink T. With the following capacities, we have capacity this should be 20. $30, $10, $5, $10. And the maximum flow is the following. So this time you get the flow for free. Just 10 units of flow. Here we have 20 units flow, and I made a mistake here. The capacity I made here this capacity should be 20, not 30. Let me correct this part. This is 20. And we have 5 units of flow here, 5 units here. Here's another mistake. I'm sorry. This one here would be capacity 20. Really have to write this a bit bigger or get new glasses. This should be 20. And we completely saturate this edge. And we have 5 units of flow on this edge. And we will have 10 units on this edge. 10 out of 10, 5. Yeah, looks good. Okay, so let's create the residual network out of this from this network and given this flow. And GF should look like this. We have, of course, the same set of vertices. And we should have 10 units left in this direction and 10 units in the backward direction. So in this case, I'm not visualizing these backward edges anymore in red. But I think by now the concept is clear. Here we have nothing left, but we have this backward edge with 5 units. Here we have 5 units left and 5 backwards. And here we have, again, 20 units backwards. What else? This one goes in the reverse direction with 5 units. And 10 units here. 20 units here. So this is how the residual network looks like given that particular flow. And so now we have to look at which nodes will be reachable from S, which in this case are. Can anyone tell me which vertices we can reach from S? I hope you can see this from this figure. Yeah. BD and S itself. So we have L will be equal in this case to that's SBD. And then R will be the rest, in this case containing C and T. And what's the capacity of the cut, of this particular cut? Yeah, it's 30, yeah. And it should be 30 because the value of that flow is also 30. And that's what we wanted. So you can see that maybe let me also write this down. The value of this flow here on top is simply the sum of the edges leaving, or the sum of the flow of the edges leaving S, which is 10 plus 20. Here the capacity of LR will be SBD. These are, so the vertices, the edges leaving SBD is this one here of capacity 5, is this here of capacity 5, and it's this here of capacity 20. We'll have 5 plus 5 plus 20. That's the minimum cut. So this is how we compute a minimum cut. We can, yeah, question? Yeah. You mean you can't reach D on a direct path from S? No, you can't. No, exactly. Because we're looking at the residual network here, right? Not the original network. We want to look at the nodes that are reachable in the residual network. So there's no edge from S to D, but there's an edge from S to B, and there's an edge from B to D. So in that sense, D is reachable from S. Sorry, what do we mean as a stroke cut? Ah, yeah. Ah, no, it's SPD. So this is basically this here, meaning if I just draw it, so SPD is this one here. This is L. Right, this one. And this is you know, all these three edges are leaving this set on the left. Any other questions? Okay, then we're almost done with maximum flows. I just want to show you one idea of an application, how you can use max flow to solve a problem that seems to be a completely different setup. In this particular case, you want to compute maximum matchings in bipartite graphs. So this sounds like a completely different task, but it turns out that it's actually the same as just computing a maximum flow. And I want to illustrate how you can model this. So for this, let me quickly remind everyone, in case you didn't hear about it, what a matching is, what a maximum matching is, and what a bipartite graph is. Who has not heard of bipartite graphs? So everyone has heard of bipartite graphs. Who has heard of bipartite graphs? Okay, everyone else? And matchings? Did anyone hear about matching before? No. Okay, then let me just write down what this is. So this is one example application of using maximum flow. The application of max flow is computing maximum bipartite matchings. So let's just define these 2 or 3 concepts: matchings and bipartite graphs and maximal matching. So the idea of a matching is that you want to match elements on one side to elements on the other side, and you want to do this in a one-to-one correspondence. So, for example, you want to assign jobs to certain computers, and you want to do this such that every job is assigned to exactly one computer. Then you want to compute a matching in the sense that if you think of a graph where these computers would correspond to nodes on one side and the jobs to nodes on the other side, you want to have a subset of the edges between computers and jobs such that no 2 edges are incident on the same vertex. So every vertex has at most one matching edge incident to it. And I will show this in an example in a minute. But let's write this down first. So a matching is typically denoted by capital M. A matching M of a graph is an edge subset M subset of E, such that at most one edge of M is incident on any vertex V. Such that at most one edge of M is incident on any vertex in V. And then naturally we want to find a maximum matching. An empty matching is a matching. We can just pick any edge, and this is also a matching, but of course we want to assign as many jobs as possible under this constraint to our machines. So maximum matching There's a matching such that for any other matching M prime, have that the cardinality of M is greater or equal than the cardinality of M prime. So it's the matching of largest cardinality in your graph, the maximum matching. Even though you've heard of bipartite graphs, let me briefly define them. In a bipartite graph, G, node set V and edge set E. The node set can be partitioned into L and R. That don't overlap. So intersection between L and R is empty. And all edges go between L and R. We don't have any edges within L, and we don't have any edges between within R. All edges in E go between L and R. Good. Here's an example of a bipartite graph. So this is a bipartite graph. We have our vertex set. We have two sides, and we have edges only between the two sides, not within. And the possible matching, not necessarily a maximum matching, but I'm just showing any matching in this bipartite graph could look like this. I could include this edge, for example. Let's connect this one also somewhere. So I have this edge, and I have, let's say, this edge, and I have this edge. I have a matching of size 3 in this case. For completeness, this is what we call L, and this is what we call R. Okay, so this is a matching in a bipartite graph, and we want to model this as a flow network such that a flow in this network will correspond to a matching in a bipartite graph. Any suggestions, maybe also based on homework, how you could do that? So we definitely need two dedicated vertices, the source and the sink. So let's try the following idea. We have this new vertex S. I'm not going to define this new net or this network formally. I'm just illustrating this through this figure. So we have this extra vertex S, and we have this extra vertex R, sorry, T, source and sink of our flow network. And we will connect S to all vertices on the left. And we will connect any vertex or all vertices on the right-hand side to our sink T. And we will assign a unit capacity, a capacity of 1 on all the edges. And we will also direct the edges that we already have between L and R. So we will not introduce any new edges there, but we will direct these edges from L to R. So here, these edges we'll get that direction now from left to right. And we will assign unit capacities to all edges. So all edges have unit capacity. And the claim is that the maximum matching in the bipartite graph will correspond to the maximum flow in this network that I've just constructed with these two new nodes and these orange edges from S to all nodes on the left and from all nodes on the right to T. We're not going to do a formal proof of this, but I think it's very intuitive and very easy to see how we can establish a correspondence between a flow in this network and the matching in the original bipartite graph, namely as follows. So if you take this matching as an example that I have indicated in green, let's just do this with a thicker color. Then consider the following paths from S to T, where I start in S and I just follow the edges with a matching in the matching and then continue the unique edge that leaves that vertex to T. And I do this for all matching edges. So I can use this edge to reach the vertex, which is incident to a matching edge. And I follow this matching edge and I leave it on this one dedicated edge to the sink. And I do the same for the third one. And these paths will sort of, build a flow of a value that will be equal to the number of edges in your bipartite matching just by this construction. The trick, or one thing that you have to be careful when you think about this, is that the flow that you're getting when you run Ford-Fulkerson will be integral because all your capacities are 1 and therefore integral, and therefore you get integral capacities. In this particular case, the flow will be 0 or 1 on every edge. And therefore, there will be a 1-to-1 correspondence in the sense that whenever you have a matching with k edges, you can create such k paths with unit flow, and therefore a flow of value k of the same value as the size of your matching. And then in the other way around, if you compute the matching, it will look like this matching in blue because you have integral flow values and you have unit capacity, so you cannot have any touching paths. And if that's the case, you can construct a matching out of this flow basically because these paths will be disjoint and you can pick one edge between L and R for each such path that carries 1 unit of flow. And this is sort of so probably just sit down for a moment and think about it, but it's based on this picture. This is sort of the idea of the correspondence between a flow and a matching, and therefore computing a maximum matching can be done by just computing a maximum flow that will look exactly like this. Any questions? Is that clear to everyone? So this is the last part of the matching. So let me just write down what I sort of hand-waving claimed here. And there's a more formal proof in the book, but if you have this picture in mind and just sort of get an idea how the flow can help you to compute this maximum flow, I think this is good enough. In this case, what you need to do to compute the maximum matching is to construct this flow network G prime that are again not defined formally, but we have these 2 additional vertices, and basically we introduce these orange edges with capacities of 1. So this is what I mean with construct flow network G prime. Then the maximum matching in G corresponds to a maximum flow in G prime. And then thing in G corresponds to maximum flow in G. Sorry, G prime. Okay. Questions? Anything about flow or cuts before we start a new topic? Yeah. Max flow? The min cuts, it's BFS, so it's also linear. You have to create the residual network in linear time in order, number of edges, and then run BFS. That's it. It's also linear, yeah. Okay, if there's no more questions, I'll start with what is called greedy algorithms. This is in the textbook. Paragraph 5. Has anyone heard of greedy algorithms before? Yeah, a question, or did you hear about greedy? Yeah. Oh, yeah. Anyone else? Greedy algorithms? Yeah, there's nods. Yeah. So greedy algorithms are very, very popular and very powerful. It's my impression that they're widely used also in application, also in our field. And when I say our field, in computational biology or algorithmic bioinformatics, whenever you talk to a biologist and you come up with a model for a biological problem, which typically is a bit nasty and much more dirty than typical max flow problems as we have formalized them, then the first kind of algorithm that biologists or anyone in application comes up with is a greedy scheme. Typically, you cast everything as a series of choices. You make a certain choice in each step to assemble a solution to your problem. And then each step, you're trying to be greedy and you try to think about what's the best at this particular point. And then after doing this, you are left with a smaller subproblem that you keep on solving until you have solved sort of the entire problem. Very natural. It's very fast, as you can imagine. I mean, typically, this is very fast because you make local choices. You don't care about sort of the global context, which very often makes these decisions much easier. And the nice thing is that in many scenarios, you can show or prove that your problem has a certain structure, such that these local choices are actually good enough to obtain in the end actually an optimal solution to the global problem. And this is a very nice property. Or sometimes you can't, but you still can prove that you get good solutions with a certain guarantee, an approximate solution. And sometimes you can. Sometimes you get a heuristic that will maybe work well in practice, but maybe without any guarantees. But those are the ones we don't sort of concerned with those in this class. Here we're concerned with greedy algorithms for which we can prove that they actually provide optimal solutions to the problem or counterexamples, as we will see. Let me just sort of write down what the general idea is of a greedy algorithm. This is something where you build up a solution piece by piece. This is the main idea. And each piece is sort of the one that looks the best at the moment when you make this particular choice. So I'll be a bit abstract in the beginning, but you will see this in an example in a couple of minutes. So an algorithmic approach. This is very typical for optimization problems, where you, as I said, can cast this problem as a series or a sequence of choices. And each choice you make to increase the benefit or the quality of the current solution as much as you can. So you're trying to be greedy in every step. And then you hope, or you're able to prove that the solution that you get in the end is sort of the globally optimal solution. Terms of choices, or each choice is made to provide sort of the best improvement possible. This is why it's called greedy. You're trying to really get the best out of every possible choice. And then you're either hope or proof that at the end, after making all these choices, you get the globally optimal solution. Yeah. Sorry? Would it be a greedy algorithm? It is a greedy. So let's see, it's a series of choices. I would say no, but let me try to how to properly argue that this is not a greedy algorithm. So you're starting with a zero flow. In each step, you're taking the maximum possible improvements with an augmenting flow. Yeah, I don't see why you would not call this a greedy algorithm. And then every time you do that, you obtain a subproblem that you don't have to No, because so what's missing here is that you actually have to keep track of previous solutions to create this residual network. So every time you do this, it doesn't depend only on this local choice that you made, but you take into account all previous decisions to create the residual network and sort of compute the best possible augmentation in the space. So it's not sort of in the greedy scheme, but maybe this is more clear once I finish this. So in the greedy scheme, it's really you make this one choice and then you don't care anymore what you did and you just sort of solve this remaining problem optimally. And this is not given in this Ford-Fulkerson algorithm. But this is, I admit this is a bit subtle. So let me think about how to explain this a bit better. But this seems to be the the part where it breaks in this case. So let's go through this example, then we can probably go back to Fort Focus and see where the difference lies. So in case you can sort of do greedy for almost any optimization problem, the question in the end is that solution that you're getting sort of optimal? And we will see that you need, in essence, 3 key ingredients to be able to show that this algorithm in the end gives you actually an optimal solution. 3 ingredients, the one that we have already mentioned, namely having this sequence of choices that you have to make. But we will see that this is not enough. We will see that we need 3 key ingredients. To show that this leads to an optimal solution. So the first we already mentioned. The first is simply that we can cast this as a sequence of choices that we have to make. And each choice leaves exactly one single subproblem that we have to solve. And each choice gives a single subproblem to solve. So here's an example of such a problem that has exactly this structure of having to do one choice at a time. This is called the 0-1 knapsack problem. Here's an example of the 0-1 knapsack problem. So in the 0-1 knapsack problem, think of a thief that has a backpack, and he can choose between different items to put into his backpack. This backpack carries a certain maximum weight, or you can put items of a certain maximum total weight into this backpack. And each item that you can choose has a certain weight and it has a certain value to it. So you can pack certain items up to a certain capacity, and once you're sort of selling these items, you get sort of a certain value back for these items. And the question is, which items should you pack into your backpack to not exceed the capacity of the backpack, such that in the end you achieve the highest value of the items that you put into your backpack. So a thief has a backpack. With limited capacity. A set of items. And each item has a certain weight and a value. The question is, how do you maximize this value? How do you pack your backpack to maximize this value? So, so this is here, say your backpack, flexible backpack. And let's say this backpack in this particular example holds up to 50 pounds. And you have the following 3 items that you can choose from. You have a very small item, a somewhat larger item, and the largest item. So the smallest item has only 10 pounds. Then you have one with 20. Sorry. With 30, the largest. And if you sell the smallest, you get $60 back. For the mid-size, you have $100. And for the largest, you get $120. So what would you do if you were the thief? If you think of this concept of making local choices, you see these 3 items, or not these 3 items, but let's say, what would your general strategy look like if you had, dollar per pound, exactly. So because only looking at the value is a bit tricky, because if it's a very large item, it takes up a lot of capacity of your backpack. If you only look at the weights, then you might pack things that are really just big and not so valuable, maybe the base of your grandmother. And so the idea is to sort of normalize the benefits, the pounds, by the weight of this item. And if you do this for the items that we show here, we would have effectively, for the first item, a value of $6 per pound. And then we have $5 per pound for the second. And we have $4 for the largest. And so a naive approach would be really in every step, pick the one that has sort of the highest per pound value. This is a naive approach. Pick the highest value per pound. And we'll go through this, I think we'll finish this example next time. So better if you have any questions. Otherwise, I think we will stop at this point.